In this lecture, I'm going to talk about the second random number generation method, the linear congruential method. Just to recap, a pseudo-random number generator is an algorithm for generating a sequence of numbers whose properties approximate the properties of a sequence of random numbers. It's used in many different places, and in this lecture, I'm going to apply it to find the area of a shape, which is the same as actually integration. So the two properties you need are uniformity and independence. That if we're generating numbers between 0 and 10, we generate all the numbers between 0 and 10 equally. Random numbers must be independent. So if there was a 2, you can't predict the next one if you don't know the algorithm. If you know the algorithm, everything is predictable. Now, there are so many issues with this. Numbers might not be uniformly distributed. You can only really generate discrete values, which you then have to map on to the continuous. The mean of the generated numbers might be too high. So between 0 and 10, the average number you'll get is 7, but it should be 5 because that's the middle of the distribution. Or the variance is too high or too low. If it's too low, that means you're just going 4, 5, 6, 4, 5, 6, 4, 5, 6, and not looking at the other numbers. If there's an autocorrelation between numbers, you can predict the number. You don't want that either. And lastly, if you go above and below, so if you go 2 up, 2 down, 2 up, 2 down, that's also predictable as well. So we've looked at the middle square method. So now we're going to look at the linear congruential method. So it's very similar to our Vigneri cipher. We take in a value, we add something to it, and we do the mod. The difference here is we have it multiplied by a. M is your modulus, a is your multiplier, c is your increment. And you just have to make sure that m is greater than 0, which makes sense. A is less than m, once again, it's modulus, so that makes sense. And c is less than m. What you always have to start with is a seed, an x0, and that also has to be less than m. And that'll generate your sequence. So you need the formula and the first point. So here we have the algorithm of it. We take in I is equal to 0, we give in the x0, n is the length of our sequence, a, c, and m are choice of the values, and we just iterate through. Very simple to program, very simple to implement. So let's do an example. 7xi plus 7 mod 10. Okay, so I've just randomly chosen those numbers, and I'm going to generate numbers between 0 and 9, because that's what mod 10 is. So put in 8 as our seed, 7 times 8 plus 7. Gives us 3. Yeah. And then 3 gives us 8. So the selection of parameters matter because now we're just having 3, 8, 3, 8 every time. So that's predictable. So the selection of the values a, c, m matter. They drastically impact how long a list of random numbers you get and how random they look. So this is our only theorem really in the course. The theorem states that the linear congruential method has a full period. So that means you'll get all the numbers between 0 and 10, for example, if m and c are only divisible by 1. So there's no coprime of them. Yeah? Next, if q is a prime number that divides m, and q divides a minus 1. Doesn't divide a, divides a minus 1. And lastly, 4 divides m, 4 divides a minus 1. If you satisfy all these 3 conditions, it doesn't mean it'll work, but if you don't satisfy any of them, it won't work. So here's our example. So if m is 15 and c is 4, they're coprime because the primes of 15 is 3 and 5, prime of that is 2 and 2. A is actually coprime to all of them, but a minus 1, which is 7 minus 1 is 6. 6 is divisible by 3. 15 is divisible by 3, so q is equal to 3 in this example. So let's have a go. So let's start with an x0 is 0, just for simplicity's sake. 7, 0 plus 4 Mod 15 is 4. Then we put 4 in. That's our new number. So we have 7 times 4 plus 4. Mod 15 gives us 2. So now 2 is our next number. 7 times 2 plus 4. Mod 15 gives us 3. Yeah. And then 7, 3 plus 4. Mod 15 is 10. 10 times 7 gives us 14. And that'll keep going and going and going. And hopefully it'll go 15 times to get all 15 numbers in the list. And then it will start repeating itself. How do we use this to generate numbers between A and B? So we have our sequence xi, and if we just divide it by m minus 1, the modulus minus 1 will generate all numbers between 0 and 1. So let's do the example. 0, our new number is 4. So our random number is 4 divided by 15 minus 1, 14, 0.28. So now that's our number between 0 and 1. 2 is the next number. Our next number between 0 and 1 is 0.1428. 3 is the next number. The number between 0 and 1 is 3 divided by 14. And 10 divided by 14 is the next number. And you keep going like this. So that's how you generate your numbers between 0 and 1. So to generate numbers between 0 and 7, you divide by m minus 1 and multiply by 7. To generate numbers between 0 and 100, you divide by m minus 1 and multiply by 100. Yeah. So here we have the generalization of it. To generate numbers between A and B, we divide by m minus 1 and multiply by b minus a and add a. Yeah. That just shifts it. B minus a is the range you're generating, and that just shifts the range. So here we have the code for it. It's only ever slightly different. You have a lowercase x that generates the sequence between A and B. The lowercase x generates the sequence between A and B. So you have two lists. You have capital X, which is the random numbers, lowercase x, which is the numbers between the range you're interested in. So how do we use this to find the area? We throw darts. So how do we do this? So I'm interested in the area of this triangle. Yeah. So what's the area of this triangle? Well, we can calculate very simply. It's half the length by the height, so the area is a half. We know the answer. But how do we do it with random numbers? So what we have to do is we have to generate a sequence of random numbers between x0, y0, all the way up. Yeah. So we have our sequence of random numbers, and we throw the dart. Now we make our sequence of random numbers, and we create our number between 0 and 1. That's where our lowercase x is. So let's start and go through an example, and then we'll look at the algorithm again. So that's our thing. So we throw a dart, and we want to throw a dart in this area here. Now, if the dart hits in the black area, that means it's in the area we care about, so we count it. If it goes into the white area, it's not the area we care about, we don't count it. So we threw a dart, it hit here, we don't care about it. We threw 10 darts. 1, 2, 3, 4 landed here. 5 landed above. So to predict the area, all we say is we threw 10 darts. 4 of them are in here. So the area is 4 divided by 10. The number of darts that landed in the area we care about. So what about 100 darts? I threw 100 darts. 46 of them landed in here. So the area is 46 divided by how many darts we threw, which is 100. Yeah. We do 1,000 darts. 495 of them landed in here. The others landed here. So the area is 495 divided by 1,000. Yeah. So that's our area. So now let's do it for 10,000. And when we get to 10,000, the area tells us it's a half. We knew the answer was a half, but now we did it by just using random numbers. So for every single one of these, we have an x and y coordinate, and we just need to know, is it below or above the line? So how do we do that algorithmically? We start with a seed. We need to choose an A and M. So C for X, C for Y, and a C. and we have a sum. Actually, that should be area. So what happens is we generate our random numbers and we create X and Y. That's going to be on between 0 and 1. And we ask is, if X is less than or equal to Y, then we're in our area. So we add, so that's just counting, plus, plus, plus. And then we divide by n minus 1 to get the area. So that's straightforward. Here we have it as pseudocode and in flowchart as well. And all we're doing is every time it's in the area, we add 1. If it isn't, you don't. So let's do another example with the circle. So to find the area of a circle, as we know, is a is equal to pi r squared. When r is equal to 1, a is equal to pi. So that's how we find out the area, what pi is. The formula for a circle like this is 1 is equal to x squared plus y squared. So if we throw a dart and it's between, it's in the circle, we count it. If it's outside the circle, we don't count it. Okay, so that's our game. So this hit here, and because it's in quadrants, you multiply by 4. So here we have our area is 4. That's not a bad approximation of 3.14, but is a bad one actually. So let's do a few more. So you see here, we did 10, 2 are outside, 8 are on the inside. So it's 8 divided by 2, multiplied by 4, 3.2. Pi is 3.14, so we're getting there. Now, we do 1,000. So all those landed in, those didn't, and we get the pi is 3.1569. It's not 3.14, but it's not so bad. 10,000. With 10,000, you see, we get the approximate area of 3.14. That's a pretty good approximation of pi just by randomly throwing darts. So here we have our code for it. So we can use random numbers to integrate. It's the same premise. If we want to find the integral from 0 to 1 of sine x pi x dx, 0.36, all we have to do is, if x and y are below the line, then we count them. If they're above the line, we don't. And if we do that, we get the value of 0.38. It's not perfect, but it's heading in the right direction. The more darts you shoot, the better an answer you get. This is the beginning of Monte Carlo. So that's the whole course. What you note is the link between encryption and the linear congruential. Very similar formulas. And that's this cryptography and random numbers are essential now, and they're used all the time in computing. So we just covered the linear congruential method, and in class we'll apply it and do examples to show how the choice of your start condition and the choice of A, C's, and M's impact how the sequence progresses.